Okay, so this is exam number 2. I'm going to go through all 3 parts. I have all the solutions written up already, and I'm just going to basically talk through how the solutions work. So for number 1, this is a related rates problem. We have 2 different ships, Tasha's and Desmond's, and we have some information about the ships, and we want to figure out how fast the distance between the ships, how fast is this distance changing at 2 a.m. So the way that I started this problem is I created 2 different pictures, basically. There are 2 points in time that are given to us, basically. There's the time at 2 a.m. that we need to figure out, and then there's the starting time. At the starting time, which is at midnight, we have that Tasha's ship is 10 miles east of Desmond's. So that's this diagram here. Desmond's ship is there, Tasha's ship is there, 10 miles east. And we have some information about how quickly and in what direction the 2 ships are traveling. So from that, we can calculate at 2 a.m. the position of the ships. So if you start off there and then you travel for 2 hours, Desmond's ship is traveling north at 20 miles per hour. So after 2 hours, it'll be 40 miles. And then Tasha's starts off 10 miles east and then is traveling eastwards at 10 miles per hour. So after 2 hours, it's going to end up being 30 miles from this starting point. And so we end up with a triangle 30, 40, and therefore the third side has to be 50 miles. And then we know that, and I can maybe draw a little bit. We know that this ship is traveling in this direction, and this ship is traveling in that direction. And so the equation that we need to describe the situation is, well, this is the abstract image. We have that x is changing, y is changing, and z is changing. And we have this equation, z squared is equal to x squared plus y squared. We then take a time derivative. So you could say this is d dt. But if all of my time derivatives, I use the prime notation for them. And so we end up with 2z prime is equal to 2x prime plus 2y y prime. And we can just clear off the extra 2's. And then plugging in, well, we know that z is 50 from here. So that's where we get the 50 x prime. And then x is 30. And so we get 30, x prime is 10 miles per hour. That's given to us from there. And then y is 40, we computed it. And then y prime is 20, which is given to us. It's 20 miles. Wow. And so then you calculate this, do some simplification, calculate it, and you get that z prime is equal to 22 miles per hour. Okay. Right. Number 2, let's keep going. So this is just implicit differentiation. So yeah, for this, okay, that's not what I wanted. Yeah, so for this, you see that the x squared y's derivative is going to be all of this. So this is a product rule, so you have a 2x times y, but then when you take the derivative of y, you get y prime, because this is an implicit derivative. And so you end up with that for the second half. Then the derivative of x is just 1, and then e to the y is going to become this e to the y times y prime. And then you solve for y prime. So I bring the parts that have a y prime in common, I bring them to one side, so that's these 2 pieces. And then I factor out the y prime. So I get this side, and then the other side, I just sort of leave around. So we end up with 1 minus 2x on the other side. And then we just divide over, which gives us this. For 3, we have 2 different limit problems. So, well, so for the first one, if you just try to plug in naively, you'll get an infinity on top and you get an infinity on the bottom. So we get infinity over infinity. That is an indeterminate form. So we can apply L'Hopital's to it. We take the derivative of the top function, that gives us 2x. We take the derivative of the bottom function, which gives us, well, we have to use product rule. We get ln of x times x over x, which is just 1. And if you plug into this, you get infinity on top and infinity on the bottom. So you can use L'Hopital's yet another time. Take the derivative of the 2x, that gives you 2. Take the derivative of ln x, that gives you 1 over x. And then that just simplifies to 2x. You can then plug in and you get infinity. So, for B, let's see. So if you try to plug into this, you're going to get the indeterminate form 1 over infinity, which means that you need to do a bit more work. So what we do is we set the whole problem equal to some variable L, and we take the logarithm of both sides. So we get ln of L is equal to, and then the log is going to pop the x out, and it's going to then apply the log to this 1 plus 5 over x, just right there. And then to make this in a format where we can use L'Hopital's, we need it to be a fraction. So we need to bring something into the denominator. And so we just bring the x into the denominator right there. Then when we plug in, if you plug in infinity, you get ln of 1, that's 0. And then 1 over x, that's as x goes to infinity, that's also 0. So 0 over 0, you can use L'Hopital's. And so then we go ahead and take L'Hopital's. We take the derivative of the top, that's going to be reciprocating the thing, and then taking the derivative of the inner function. So the derivative of 5 over x is negative 5 x to the negative second, which is right there. Then we take the derivative of the denominator, that's going to be negative x to the negative second. And this simplifies a little bit. We can cancel, right? You can cancel the x squared in the denominator with the x squared in the denominator here. Just imagine multiplying both top and bottom by x squared. These two will cancel. Then you also have a negative and a negative, which also cancel. And so then you have this as the limit to evaluate, which you can go ahead and plug into. So 5 over infinity is going to become 0. You end up with just 5. But now you have to look back on the original problem. Like, what did we actually find? This stupid thing. Okay. So what we actually find is that ln of L is equal to 5. And so we end up with ln of L is equal to 5. We then exponentiate both sides to exponentiate over e. And so you get L is equal to e to the 5. And that's the final answer for the problem. So that was part 1. Next, we have part 2. So for number 4, okay, so it says that we have a sphere and we're going to paint it, and we want to estimate the volume of paint needed. So it's basically volume of a sphere, and this is the radius given, and this is going to be the change in the radius. The paint is going to be this thick. So what we do is we use the formula for volume of a sphere, 4/3 pi r cubed. We take a derivative of it, and so it's going to look like this. If we write it in the format that is used for like differential forms, differentials, it's going to look like this with the dv and the dr. Yeah, and then you can plug in. So r squared is equal to 10. R is equal to 10, so r squared is 100, and the dr is just given. Then you just multiply, and then so this is going to become 0.1 here. 0.1 times 4 gives you 0.4 pi. And then lastly, you should put units. So 0.4 pi meters. It should be meters cubed, actually. Yeah, that's my bad. Meters cubed is what it's actually supposed to look like. So, yeah, it should look like that. Okay. Since this is a change in volume. Okay. Oh. going. So for number 5, linearization. Okay, so you have to recall the formula for linearization. So that's L of x, that's the function of linearization, is going to be g evaluated at the number plus g prime evaluated at the number, x minus, and then the number. So normally we use a, but here we specifically have x equals 8. So our a is 8 in this problem. And well, we need to calculate g of 8 and g prime of 8 in order to actually find the exact line that we're looking for. So plugging into the cube root function 2, or 8, we would get 2. And then for the derivative, well, it requires a little bit more work. We think of this as x to the 1/3 power, take the power rule. So then we get 1/3 x to the negative 2/3 power. And then we rewrite this. So I can view this as in the denominator, the cube root of x, and then squared. So that's just me rewriting this negative fractional power. And why is that useful? Well, because then I can plug in more easily. So if I plug 8 into this, I'm going to get 2 here, and then I'm going to square the 2. So we get 3 times 4 in the denominator. And so g prime of 8 is 1/12, g of 8 is 2, and then we just have x minus 8. So we would just have this as our linearization. And then the next thing is we need to use the linearization. So, I mean, it really starts here. Why does it not hold on to the radius? Yeah, but it really starts on this side. This is just sort of setting things up to say like that this number is actually g plugged in, g of 7.8, but that the linearization is approximating g at values that are close to 8. And so those are just like setup pieces of information. The actual calculation is that L, we plug into L, the function L that we found in the previous part. We plug into it 7.88, and then we go ahead and calculate it out. So the thing is that you need to subtract 7.88 from 8 carefully. And so when you do that, you get negative 0.12. Then you divide, so you get 0.01, and then you subtract, so you get 1.99. For number 6, find the absolute max and min value on this closed interval. We've got this function L. So the process is that you find the critical points that lie inside the interval, and then you plug into the original function the critical points and the endpoints in order to figure out what the absolute min and max values are. So we take the derivative, we would get 1 minus √2 cosine x, and we would set that equal to 0 and solve to find the critical points. And so we go ahead and we calculate that out. So cosine has to be equal to 1/√2, which if you rationalize the denominator, you get √2/2, just in case the 1/2 doesn't look familiar. So you have √2/2, and you have to think, when does cosine equal that value? Well, the first angle that comes to mind should be the 45-degree angle, the pi/4. And then the second angle that should come to mind is negative pi/4, and that's because cosine is positive on these two quadrants. So we would have these two values, but then notice that because negative pi/4 does not lie inside this interval, it's immediately excluded. And so we end up having 3 places that we want to plug into this L of x. We want to plug in 0, pi/4, and pi. And when you go ahead and do that, you get these values, 0, pi/4 minus 1, and pi. And then the one thing to think about is the fact that this is actually a negative value, which makes sense because pi divided by 4 is, well, pi is 3.14. So pi/4 is going to be some number less than 1. So then when you subtract 1 away from it, you're going to get something negative. So you can deduce that this value is negative without using a calculator. And so that tells you that this holds the absolute min, and the absolute max is going to be pi. And if you wanted to, you could write these in coordinate form. So this, so if you were to write this in coordinate form, you would have this as pi over 4 comma pi over 4 minus 1, and then the absolute max would be pi comma pi. So if you wanted to, you could write it in this way. I just didn't bother to do that. Okay. Right. For part 3, number 7. So this one is a bit involved. We have an open-topped cylindrical garbage can that is made out of 12 square feet of material. And we want to figure out the dimensions that will maximize the volume. Okay, well, so first of all, the volume formula is pi r squared times h, the height. And that's because the base is the area of the circle, which is pi r squared. And then the next thing is we want to do something with this 12 feet squared. So this is measuring surface area. So we would have the bottom of the can, and we would also have the side of the can. So 12 is equal to, and then this 2 pi rh is the measurement of the rectangle that goes around the cylindrical garbage can. So the height is h for the rectangle, and then the length is actually the circumference of the circle. So that's going to be 2 pi r. So we have 2 pi r times height. And then for the bottom of the can, we have pi r squared. So we have this equation coming from the surface area. And what we can do with that, there should kind of be a divider for this. What we have for the when we calculate this, we solve this for h because we want to replace out this h in the volume formula. So we subtract over the pi r squared, then divide by 2 pi r. We end up with this formula for h, which we then plug in to the volume formula, and then we just try to cancel things out. So we are already seeing that this is supposed to be volume, a function of r, and there's some cancellation, and you should end up with 6r minus pi over 2r cubed. And here I'm saying something about what the possible values for r what they can actually be. So 0 to infinity. Well, technically speaking, r can't go larger than 12 over pi, root of 12 over pi. And the reason is because if it is root of 12 over pi, you end up using all your material on the, all the material gets used on the pi r squared part, on the base of the garbage can. And so you have no material left over for the height of it. That's basically you just set h equal to 0, and then you solve for r, and then you end up with this as being the largest amount. But we can kind of just imagine it goes from 0 to infinity. It turns out that we can just justify it using the second derivative test, which I'll explain in a minute. So we have this formula for volume in terms of r. And what we do is we take the derivative and set equal to 0. So derivative set equal to 0 and solve. So we end up with 4 over pi is equal to r squared. We then take a square root of that. So you get 2 over root pi feet as being the r value, the value for r that you expect it would maximize this volume. And then you just have to check it. So, and I also calculate like what the h value is. So you just take this value, plug it into the relationship between from r to h to get the h value. So h is also 2 over root pi. Now for the justification, though, to justify that this is actually the absolute maximum volume that can occur, what you have to do, you can use the first derivative test, you can use the second derivative test. These are the derivative tests for the absolute extreme values. Since the domain in question is actually open, it's somewhat a technical consideration, but you kind of can't put r equals 0 into this. So because if you plug if you try to set r equal to 0, in a way that's like saying that you're trying to make all of the surface area, the 12 feet squared surface area, trying to make that be be the side area. But the thing is, if r is equal to 0, then the whole thing degenerates, the whole cylinder degenerates in such a way where it's like if you have no surface area, and so 0 kind of can't be plugged into this physical situation, and so you have an open interval 0 to infinity or 0 to root of 12 over pi, which means we can't use the closed interval method. So you should use first derivative test for absolute extreme values or the second derivative test. The second derivative test is pretty easy to use since the first derivative here just is a polynomial. So taking the derivative of this polynomial, 6 minus 3 pi over 2 r squared, taking that derivative is pretty easy. Just you end up with minus 3 pi r. And you can immediately conclude that this is going to be negative since r is a positive value. Right, the r value, the value for r is going to be some positive number from 0 to infinity, and so this expression is always going to be negative for the possible values of r. Therefore, the second derivative is always negative, which means that this is concave down, and since it's the only well, since the second derivative is always negative, you know that the function, this man, why does it keep, oh, the scroll, the v, this tells us that v of r, it looks like a parabola. It's concave, it's always concave down. Then the critical point that you found has to be an absolute maximum, and so absolute maximum by technically the second derivative test for absolute extreme values. Okay. All right. Next we have 8. So we have to carefully look at this function that's given to us. And so we have that v prime. This is the graph of v prime, and we need to read off information about it. So firstly, when is it increasing and when is it decreasing? So increasing means that the derivative is positive. So that's going to be, positive is going to be this part and this part, since the function is positive along these intervals. So -3 to 1 and from 5 to infinity. Decreasing is going to be the complement of that. So -infinity to -3 and from 1 to 5, which is written there. And then for local max and local min, well, that's about the transition points, right? So these things occur where the first derivative is equal to 0. So we have like these points to consider. And then we just think about how the transitions work. So if this is going from negative to positive, then it looks like that. And so that means it's a local min. And same with this point. This is also a local min. Here, this is positive to negative, so it looks like that. So this is a local max. And so 1 is a local max, and then -3 and 5 are local mins, or places where they are local mins. For concavity, we visualize taking the derivative of this. So the derivative is going to be positive along this portion, and also this portion, and it's going to be negative along this whole portion. So it's positive along these two parts, and so we have -infinity up to -1, and from 3 up to infinity. And concave down is going to be complement, so it's going to be from -1 to 3. So that's where the derivative is negative. And then when does it have inflection points? Well, that's going to be when the derivative is equal to 0, which happens here and there. And so you just have to write down the x coordinates, so -1 and 3. Okay. Next, we have a second derivative function. Oh, well, we have the second derivative w sketched for us, and we have to read information off of that. So firstly, it's asking about concavity. Well, the thing is that this w prime is basically, or the second derivative, double prime, is measuring concavity. So it's concave up if the second derivative is positive. So that's where this graph is positive, which is in these two regions. So we have minus infinity to minus one, and also from 3 to infinity. And then concave down is everything else. It's where the second derivative is less than 0. So it's -1 to 3. That's concave down. And then inflection points, well, inflection points are when the second derivative is equal to 0, which happens here and there. So -1 and 3, which is what I've written. Okay. Next, number 10. So this is worth 4 points, so it might make sense to do a bit more work than what I've done here. It might make sense to actually show some more of the calculation that goes into this limit, where you, I guess, divide top and bottom by x to the 9th, and so you end up with 3/11 when you take the limit. But I think that primarily what we're going to what's going to be asked for you to find is to actually write this as an equation of a line. So y is equal to 3/11 is a horizontal line. Yeah, but it would be very helpful to also see like that you have some kind of a limit written, like that you know that how are you going from this function to 3/11. Well, what you're doing is you're evaluating a limit as x goes to infinity plus or minus of the function, and that gives you this value 3/11. Okay. Right. Then I think 11 is the last problem. Yeah. So you want to well, there's a lot to talk about. So the domain of f, what we do is we look at this function f and we think, when is it undefined? Well, it's undefined at x equals 1, but everywhere else it's totally valid to plug into. And so your domain is just everything except for -1. So -infinity to -1, union -1 to infinity. For the y-intercept, you plug in x equals 0 into this, so you get 1/1, so you get 1. For the x-intercept, you let y equals 0, so imagine that this is 0, and then, well, you can multiply the denominator over, and that's basically then asking, when is e to the x equal to 0? And the answer is nowhere, right? This equation never happens. E to the x equals 0 never happens. Okay. Next, vertical asymptotes. So that's just looking at, well, yeah, when is the denominator equal to 0? So that's at x is equal to -1, which is what I've written. And then for E, horizontal asymptotes. Well, for this problem, it's a little bit more complicated than usual. And that's because this e to the x is a bit, well, yeah, it's a bit lopsided. So e to the x is a function that looks like this, right? It approaches 0 as x goes to -infinity, but it approaches infinity as x goes to infinity. And so that kind of makes it behave differently in the two different directions, which is why I calculate two different limits. I calculate the two limits separately. So if you let x go to -infinity of the function, then e to the x is going to approach 0, whereas the denominator is going to approach infinity, 0 over infinity, which is actually just equal to 0. So this is not an indeterminate form. On the other hand, if you're approaching positive infinity, then e to the x goes to infinity, and the denominator is going to go to infinity. And so you have infinity over infinity. That is an indeterminate form. And so technically, to calculate this, you want to use L'Hopital's. So then you end up with e to the x over 1 as x goes to infinity, and that is equal to infinity. So if you go towards minus infinity, if you approach if you go infinitely to the left, you approach 0. If you go infinitely to the right, you approach infinity. And so we actually have a horizontal asymptote of y is equal to 0, although it kind of only shows up in one direction, which is why in the graph of the function, I actually only dot it in one location, and I see that I'm scrolling things, so I better clear that. Okay, right, so that's up to the horizontal asymptote. Next are the functions f and g. So in order to calculate that, I needed to do a sign chart for the first derivative, and the first derivative is given to us. So first of all, the tick marks are what I would calculate. And so the denominator is going to give us a tick mark of -1. The numerator is going to give us a tick mark of 0 because, well, x equals 0. X can equal 0, but e to the x cannot. And so the e to the x doesn't contribute anything. Just this x contributes something. And so we have these two tick marks, and then we can test the intervals. So when we plug something positive in, all three pieces are positive. When we jump over the 0, this x is going to turn negative. E to the x is always positive. This x is going to turn negative, and this doesn't change. And so we have a sign flip, so this becomes negative. Next, when we jump over the -1, well, this x plus 1 would change its sign, but because it's being squared, that doesn't introduce a sign change into the overall function f prime. So jumping over this -1 does not change the sign, so you get minus minus. So this is the sign chart, and then you just read off the information of increasing and decreasing from the sign chart. Increasing is when the derivative is positive, 0 to infinity, and decreasing is when the derivative is negative, so -1 to, or minus infinity to -1, and from -1 to 0, which is there. Okay. Then we have the second derivative. So for that, we need to look at the function for the second derivative, which is also given to us. And so we have to draw a little sign chart, and the only tick mark that we can place is actually -1. The denominator, again, can be equal to 0, but now this x squared plus 1 is never equal to 0. At minimum, it is the value 1. E to the x is always positive, so it also doesn't contribute anything. So we just have this one tick mark, and then we can just do the sign chart. So if I plug something that's greater than -1, everything is positive. All three of these parts are positive. If I jump over the -1, this x plus 1 is going to change in sign. Because this is cubed, the whole denominator is going to change in sign. That's going to cause a sign flip for f double prime, and so there is a sign flip when you jump over the -1. Okay, and then that answers J and K. So concave up is -1 to infinity, and concave down is from -infinity to -1, just by reading off the positive and negative from the second derivative. The h and I are coming from the first derivative, so I didn't realize that just now. So this is x equals 0 has a change in sign on the first derivative. So you're going decreasing followed by increasing, so that makes a V shape, which means that this is a local min. So we have 0, 1 as being a local min. X equals 0, and then just plug 0 into the function, which is actually already done here since we have this y-intercept. And so this is a local min, and there are no local maxes, since a local max would show up on the first derivative as being a transition from a plus to a minus. We don't have that kind of transition, so we don't have a local maximum. Okay. So this could have said something about point of inflection, because this -1 technically is a point of inflection, but it just didn't do that. Maybe that's because you would have had to then plug -1 in, so you get 1 over. Wait, no, actually, no. -1 is an asymptote. Yeah, okay, so that's why there's no point of inflection question. Okay, that lastly, you try to gather all that data together to sketch the function. So I guess what I'll do is I'll try to do that live on top of the pre-existing graph. Okay, so the first things are that we got from the problem are that we have this point 0, 1. We have a vertical asymptote x equals -1, and we have a horizontal asymptote y equals 0. That seems to happen only when you go to -infinity, not when you go to +infinity. And so that's just information from, I'm going to scroll up, from here. That's all that really gives us. Then the rest of it is going to be from using the first derivative and the second derivative to piece everything together. So to the left of -1, we are decreasing and concave down. So that gives us this part of the graph. And then to the right of -1, we're always concave up, and we are decreasing to increasing. And so that gives us something that looks kind of like this. So you just have to make sure that you make that 0, 1 look like a local min when you sketch this kind of curve. I suspect that this actually grows very quickly as it goes up, not quite so slanted, although you could make it look however you want to. What's the graph actually? Yeah, e to the x over x plus 1. Yeah, so this should grow very quickly here. And so, yeah, that's what the function looks like approximately. And so I guess that's it.